Alright, so in this video we introduce a new chapter, differential equations, a very brief introduction to it. Differential equations is a really big subject, and we are just going to look at basic intro, just a couple of methods to solve those kind of equations. First of all, let's define what a differential equation is. So differential equation, it's an equation that involves derivatives. Okay, so where are differential equations? Well, they're practically everywhere in which a change between two quantities is involved. Okay, that is those rates of change. So these are heavily related to population growth, spread of an epidemic, reduction of air pollution, and even a lot of applications of finance and engineering and other sciences. Okay, let's define and rather distinguish between an algebraic equation and a differential equation. So let me write this very simple algebraic equation. What do we do to get the solution to this equation, that is to solve for x? So we do the inverse, or rather the opposite of the operation that we see with the number 5, that is subtract 5 to both sides and then get x equals -3. So -3 is the solution. Okay, how do we know? Well, plug it back in. -3 plus 5 equals to 2. So -3 plus 5 equals 2, which equals 2. So that's how we know that is the solution to the equation. Okay, now let's make a distinction between that and a differential equation. So again, a differential equation, just briefly, let me give the simplest example, dy dx. So that is the derivative of some function y with respect to x. The derivative is x. So what did we do on the previous example on the algebraic equation? So we moved the constants to the right-hand side of the equation, and we kept the variable x on the left-hand side. So here we are going to have the y terms and factors on the left-hand side of the equation, and everything that has an x, move it to the right hand side. That is, I'm going to multiply both sides by dx, and then I'm going to do the opposite of the differentiation. The opposite of the differentiation is the integration. Here you can just say that the integral cancels the differential and we get y by itself, and then the integral of 2x is simply x squared plus c, which is some constant of integration. Okay, how do we know this is the correct solution to the differential equation? Well, in this case, in the previous case, we plugged in the number x equals 3 here. So in this case, we are going to substitute, well, in this case, not the function. In this case, we need to find the solution to the equation. So dy dx equals the derivative of x squared, which is 2x, plus the derivative of a constant, which is 0. Okay, and let's plug this in here, this derivative, plug it in here, and hopefully both sides of the equation match. So dy dx, which is 2x plus 0, the derivative of the constant, is that equal to 2x? Of course. 2x equals 2x. So that is the solution. So in a nutshell, when we solve algebraic equations, the solution to an algebraic equation was a number, a constant. As opposed to a differential equation, the solution will not be a constant, will be a function whose derivatives and the function itself will check both sides of the differential equations. All right, what about the solution? So we need to distinguish between general solutions and particular solutions. So on the previous page here, we got the solution to the differential equation, which was y prime or dy dx equals 2x. And then we found the solution, which was y equals x squared plus c. But that plus c could be anything. Okay, so in this case, the solution that we obtained was the general solution. General solution, y equals x squared plus c. Now, suppose we don't have that c there. The function that we have is essentially a parabola. So let's write down a few particular solutions. So that is a function in which c it's no longer there, but actually a number. For example, y equals x squared plus 0, y equals x squared plus 1, y equals x squared plus 3, y equals x squared minus 2. Those are particular solutions. So what are we getting here? Here we are getting family of solutions. And here what do we have? Specific members of the family depending given certain conditions. We are going to talk about those conditions that give rise to particular solutions. So let me just grab this real quick. So one solution to the differential equation is the parabola that passes to the origin, and then another solution, the parabola shifted up 1 unit, the other one shifted up 3 units. Okay, these are not perfect parabolas. And then one parabola that is shifted 2 units down. Okay, and so on and so forth. So there's infinitely many possibilities of particular solution depending on the condition. Again, we're going to discuss about that later in the chapter. All right, verifying a solution. So we're not going to solve differential equations yet. So first, in order to verify that a function is a solution, all we have to do is to find the required derivatives and then plug in or substitute on both sides of the equation and be sure that both sides match. Otherwise, then it is not going to be a solution to the equation. So, okay, so in this case, as an example, they're giving us one function right here, and they're asking us whether this function is solution to that equation, to that differential equation. Okay, what are we going to do here? Notice that the differential equation is calling for the function itself, its first derivative, and its second derivative. So we need to find the first and the second derivative of that function and then plug everything in to the given equation. So y prime will be the derivative of the exponential 2e to the 2x minus e to the negative x. The derivative of -1 is 0. And then y double prime, it will be 4e to the 2x and plus e to the negative x. Let me highlight with the corresponding colors just so you can see where am I going to plug this in. Okay, now let's plug in the second derivative right here. Let's plug in the first derivative right here, and the original function, let's plug it in here, and hopefully both sides match. So we're gonna have 4e to the 2x plus e to the negative x minus, careful with parentheses, 2e to the 2x minus e to the negative x, okay, minus 2 times the original function, e to the 2x plus e to the negative x minus 1 equals 2. Okay, highlight just so you can see where each is coming from. Okay, and let's combine like terms. Let's get rid of parentheses, and so we can do that. Okay, so we distribute the negative sign here, distribute the -2. So what are we going to get? Okay, the first two terms remain the same. 4e to the 2x plus e to the negative x minus 2e to the 2x plus e to the negative x minus 2e to the 2x minus 2e to the negative x plus 2. Is that equal to 2? Let's find out. Okay, so this is what are we going to do here. Okay, so here 4e to the 2x cancels with -2 minus 2 with -4e to the 2x. And at the same time here I'm going to get e to the x plus e to the x, that's going to give me 2e to e to the negative x plus e to the negative x is going to give me 2 negative e to the x, which cancels with this -2 e to the negative x, leaving me with only 2 equals to 2. And notice how this checks so that this is a solution to the differential equation, because at the end we get both sides the same. Okay. Otherwise, if you get something like 2 equals to 3 or 5 equals to 0, well, something weird went on. Double check your calculations or call it a no solution. Okay. All right, methods of solution of differential equations. By the way, the equation that we just looked at is called a second order differential equation. Why is it called a second order? Because the highest derivative, it's a second order derivative. That's why. If we had, for example, the third derivative of the function, then it would be a third order equation or a seventh order equation, etc. All right, so the list that I have here of methods of solution is at least all the methods that I know that are out there. Okay, it's a huge list. Maybe there's more. Okay, let's name them. Okay, separation of variables, which is one of those that we are going to do. And then homogeneous equations, we're not doing that one. Exact equations, we were going to do, but at the end I don't want to do it. Not too much time. Linear first order equations, that one we do. And Bernoulli's, Riccati's, clear out, D'Alembert, Lagrange equation, reduction of order. That's for higher order equations. And then higher order differential homogeneous equations with constant terms, we do that one. We're going to do that one, and then later I will tell you what homogeneous is. And then there's a higher order non-homogeneous. There's actually 1, 2, 3, 4, 5 methods to solve those huge types of equations. And then Cauchy-Euler's equations, and then there are solutions of differential equations using power series. And it's pretty much all these methods right here are involving power series. Okay, and the last one, the Laplace transform, okay, which is covered in a regular differential equations course. There might be more methods that I'm not aware of. However, these are the ones that I've seen before. This is the list. Okay, sadly, due to time constraints and due to the scope of the course, we just cover these 3 methods. Okay, and just like systems of linear equations and nonlinear equations that we cover in an algebra class, there's also systems of differential equations that are solved by many methods. I didn't include them in the list right here, but know that they exist. Okay. Separation of variables. So how do we perform separation of variables? Well, an equation is separable if it can be written in this form. That is dy dx equals f of x divided by g of x. So essentially, what do? We cross multiply this to get dy, no, not dy, to get g of y dy equals f of x dx. And then we do the inverse of it, which is integrate both sides, which is essentially what I did on the very first example. Okay, let's solve the first equation by separating the variables. All right, so this is what I'm going to do. Just like we solved the numerical equation, the algebraic equations rather, we keep the variable on the left and the constant terms on the right. Here we are going to keep the dependent variable on the left and keep move the independent variable to the right. So I'm going to multiply both sides by dx to get the following: dy equals 2x y squared dx. In this case, I'm going to divide both sides by y squared, and that's going to separate the variables. So I'm going to be left with 2x dx and dy over y squared, which is the same as y to the negative 2 dy. Okay. So now that we have the variables separated, what do? Integrate both sides. Okay, so the integral of y to the negative 2 is y to the negative 1 divided by negative 1, and the integral of 2x is simply x squared plus c. Okay, the question here is, notice I didn't put the constant of integration on the right hand side. Let me do this on the side to explain why I didn't do that. Okay, so for example, the integral of y dy, let me make this simple, equals the integral of x dx. Okay, let me actually put it 2. So this is going to be y squared plus, let me call it c1, equals x squared plus c2. Okay, what am I going to do? I'm going to move the c1 to the right hand side. X squared plus c2 minus c1. The difference between the constant is just some constant that we globally call it c. So that's why from now on, for this method, we're just going to add the the c only to the right hand side. Okay, let me finish rewriting this. This is going to be negative 1 over y equals x squared plus c. Notice this is the same as divided it by 1. What am I going to do? I'm going to cross multiply to get I'm going to get y equals negative 1 over x squared plus c. And that's the general solution. So in this case, we're not looking for a particular solution. We're going to do that on a different example. All right, find the general solution of the differential equation y prime equals e to the x plus y. So first we do two things. Number one, change the notation for the derivative symbol to dy dx so we can separate the variables, and then I'm going to use loss of exponents e to the x times e to the y. I'm going to separate the variables, so I'm going to multiply both sides by dx. And then I'm going to divide both sides by e to the y. Use a different color to contrast. So cancel this guy. So now we basically have the variables separated. We're going to be left with e to the x dx on the right hand side of the equation. And on the right, we can move this e to the y with negative exponent. Now that we have separated the variables, we can integrate both sides. So the integral of e to the negative y is going to be negative e to the negative y equals e to the x plus c. Okay. So now then our goal is to solve for e. What am I going to do to solve for e? First of all, I'm going to divide by negative 1 on both sides. Okay. To get e to the negative y equals e to the x, actually negative e to the x, and in this case plus c. I'm going to keep the plus c. You might wonder why, because this c divided by -1, well, we have a constant divided by -1, which is still any constant. So in this case, it's irrelevant for now, but it will be that the value of the c will be relevant when we have an initial condition. Okay, so let me rewrite the order of this. Let me write it as c minus e to the x, e to the -y on the left-hand side. Now, to solve this equation for y, we need to get rid of the e. So we need to take ln on both sides in order to eliminate the exponential, giving us a negative y equals ln of c minus e to the x. And divide both sides by y. By -1 to get y by itself. That is negative ln of c minus e to the x. Final answer. Okay, let's do another examples. Let's do y prime equals y over x. Okay, so first of all, let's change the symbol of the derivative to dy over dx equals y over x. Okay, let me multiply both sides by dx. dy will be y dx divided by x. And I'm going to divide both sides by y. And in order to get the y's on one side and the x's on the other side. Now that we have the variables separated, integrate both sides. Integrate both sides. The integral of 1 over y will be ln of y equals the integral of dx over x, that's ln of x, plus c. All right. What are we going to do here to solve this equation? Well, the inverse of the natural log this time will be exponentiating both sides of the equation base e. So the exponential cancels the ln, and we get y equals e to the ln of x plus c, but in this case I'm going to use e to the c. I'm going to use loss of exponents. Okay, so there's two things that are going to happen here. Number one, this e to the ln cancels as well to give us y equals x, and this e to the c is just another constant. So just call it c. Okay, so this will be y equals cx. That is the solution to the equation. Okay. All right. So let's see. Let's look at initial value problem. Initial value problem, it will have more than one thing in it. It's going to look like a system of equations. So this is the actual differential equation, and this is the initial condition. So what are we going to do? So for examples 1 through 3, we found the general solutions only, that is the family of solutions. So now we are going to find a general solution first for this equation, and then the specific member of the family of functions that passes through the point x equals 0, y, 3. That's what this means. Okay, so let's solve the equation first, and then we find a particular solution to it. All right, so this is what, let me write the equation again. Y e to the x plus y squared minus 1 dy dx. I'm going to change the symbol of the derivative, equals 0. I'm going to move this whole term to the other side. So y squared minus 1 times dy dx equals negative y e to the x. Okay, I'm going to multiply both sides by dx. move it there to start separating the variables. This is going to give us y squared minus 1 dy. We should have parentheses around, equal to negative y e to the x dx. Finally, we are one step away to get the separation of variables on both sides. Okay, what did we do here? Multiply by dx, cancel. And let's divide both sides by negative y. Okay, so on the right hand side we get e to the x dx. On the left hand side, y squared divided by negative y, that is going to give us negative y, and negative over negative 1 over y, this is plus 1 over y. Let me write down the negative term first and the positive term and then the negative. I think it'll be easier to read. And I forgot the dx right here. Okay, so now that we separated the variables, integrate both sides, okay? So the integral of 1 over y, we already did that one before, that's ln of y, minus the integral of negative y, the integral of y rather, it's going to be y squared over 2 equals the integral of e to the x, which is simply itself e to the x plus c. Okay, notice in this case, in the previous cases, we were able to solve explicitly for the dependent variable y. In this case, we won't be able. Don't even try. You won't, trust me, you won't be able to solve this equation for y. So just leave it in implicit form. In some cases, we leave the equation in terms of an implicit form. Okay, so now, by the way, there was a little typo here. This one was supposed to be 1, not 3. Okay, a 1, not 3. It's corrected on the PDF file, but it was not here. So let's use the initial condition with y of 0 equals 1. That is when x equals 0, y equals 1. We are going to plug in 1 wherever we see the letter y. So ln of 1 minus 1 squared over 2. Okay, let me use orange for the 1. Equals e to the value of x, which is 0. I'm going to use green. Okay, now what is ln of 1? Isn't that a 0? And then minus 1 squared over 2, which is just negative 1/2, equals e to the 0, which is 1, plus c. Okay, so when solving for c, the constant of integration, we get c equals negative 1 minus 1/2, which will add up to negative 3/2. So this is the general solution. Now the particular solution, that is the member of the family that of the functions that passes through the point x comma 0 y equals 1 is ln of y minus y squared over 2 equals e to the x minus 3/2. Okay, and that's the answer to this equation. This is actually the textbook example. For some reason they have a different answer, but I will go with this. Okay, so these were examples of separable equations. Let's look at first order linear differential equations. In this case, these are equations that are not separable. Okay, and a first order linear equation, it's an equation that can be written in this form. The derivative of the function, which is y prime, plus some function p that multiplies the function itself equals some other function q of x. In this case, as you will see, it's not going to be separable equation, and the solution to the equation is it will be given by this huge expression. Holy, okay. What are we going to do here? Looks like a really big formula. However, we can simplify a lot of the work for this type of equations. I would like you to observe something in common. Notice here we have this e to the integral of p dx, integral e to the integral of p dx. Okay. What we can do is do that calculation first and then put it in the formula. Okay, so let's look at one example to show how this works. Okay, so p of x, let's identify p of x, which is whatever multiplies y to the first power, which in this case is -3, and q of x, whatever is on the right hand side, which is 6. Notice this equation is in the correct form because the coefficient of the first derivative is a 1, as we are supposed to have to. If it's not a 1, then we will have to divide both sides of the differential equation by whatever is multiplying the y prime term. Okay, so let's evaluate the quantity in green, the e to the integral of p dx. This is e to the integral of -3 dx. Focus only on the integral on the exponent, that is e to the -3x, that e to the -3x. We don't put the plus c here. Okay, so let's write down the solution to this equation. So this is y e to the integral p dx equals the integral of q e to the integral of p dx dx plus c. Okay, I'm going to copy this formula because I may need it for the rest of the examples. Okay, Control C. We will need it later. Okay, and notice how we calculated this using green. Okay, oops, something happened here. Okay, so let me all right, so this quantity right here, e to the -3x, we can just plug it in and substitute with this whole symbol because that's what it is. That's what we calculated here. So what do we have? Y, and then instead of this quantity in green, we just write e to the -3x equals to the integral of q. But what's q? Q is just 6 times e to the -3x dx. And notice this already has a plus c. That comes from the method of solution. I'm not going to do the derivation of the formula, but there is a justification to this formula. So in this case, we're just going to use it because we know it works. Okay, so the integral of e to the -3x will be, so first of all, y e to the -3x equals 6 e to the -3x over -3. That is the integral of the exponential function, and this 6 is just a multiple constant plus c. Let me continue here, and I'm going to get y e to the -3x. And notice how 6 over -3 reduces to -2, e to the -3x plus c. Finally, we need to solve for the quantity y by dividing both sides by e to the -3x, e to the -3x, e to the -3x. Okay, so cancel, 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 cancel. So we get y equals -2 plus c times, okay, notice time not divided by, this exponential function with negative exponent in the denominator can be moved to the numerator with positive exponent, e to the 3x. And that is the general solution for this equation. Okay, let's look at another example in which we identify our p of x and our q of x. So p of x equals negative 2x and q of x equals x. Okay, so first let's calculate the e to the integral of p dx part, okay, which will be e to the integral of negative 2x dx. Focus on the integral in the exponent, integrate that guy, the exponential base e just remains there, so the integral of negative 2x is negative x squared. Okay, so let me write down the formula here just to show you what are we going to write next. So we already have this quantity. Well, let me change color here. Let me use this purple right here, okay, just to denote that we were focusing only on that integral. Okay, so this quantity that I'm highlighting in green, e to the integral of p dx, e to the integral of p dx, we are going to replace it with this e to the negative x squared. So y e to the negative x squared equals the integral of q, which by the way is x. Careful, notice I'm going to highlight it with yellow as we did earlier. So that's x times e to the negative x squared dx plus c. So let's evaluate this integral that we have on the right hand side first. Notice in this case we are going to require a u substitution in which u will be negative x squared and the du will be negative 2x dx. So we have the x dx except that we don't have the negative 2. We need a negative 2 provided we divide a negative 1/2. We put a negative 1/2 outside of the integral. So we are going to have y e to the negative x squared equals a negative 1/2 integral of u. I mean not u, that's only e to the u du. But what is the integral of e to the u? Isn't it just e to the u, because the integral of an exponential function, it's itself the exponential function, negative 1/2 e to the u, oh I forgot the plus c here, and plus c. And let's just go back substitute, so that's y e to the negative x squared equals negative 1/2 e to the negative x squared plus c. What do we do next? Divide both sides by e to the negative x squared to get the y by itself. So cancel, 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 cancel. So we get y equals negative 1/2 plus c divided by e to the negative x squared can be written in the numerator with positive exponent. So c e to the x squared. And that is our final answer. Okay, let me write this e better so it's more legible. All right, so that is the general solution. Okay, let me do another example. An example in which the equation is not written in the correct form. That is, how do we know it's not in the correct form? Because notice this term, the leading term, x, y prime. So we need to have that y prime by itself with no factors other than just that invisible one. So let's get that done. We can get that done by dividing both sides or everything by x. Turning the equation into y prime plus 2 divided by x, y equals x squared over x, that's just x, in which p of x equals 2 over x and q of x equals x. Okay. Now, how are we going to solve this equation? Well, we need to evaluate first the quantity e to the integral of p dx. This one is going to be a very interesting one. So e to the integral of 2 over x dx, okay, this is the same as saying e to the 2 times the integral of dx over x. But what is the integral of dx over x again? That is ln of x. So I know what you're thinking. Maybe you want to cancel this exponential with the ln, but we cannot do that yet because we need to have the ln to have a coefficient of 1. In this case, it has a 2. So what are we going to do? We're going to do basketball here. The basketball rule for natural logs. And e to the ln of x squared, which is now permitting us to eliminate e with ln, so x squared will be that part. Okay, so let's write down the formula to see what are we going to do now. So this quantity that we got here was no other than e to the integral of p dx, which is this. I'm going to replace with that in a moment in the next step. So y times x squared equals the integral of q, which is x. Okay, let me highlight just to show you where it is coming from. Q comes from here, and x squared, which is the quantity in green, plus c. Multiplying these together, we get y x squared equals the integral of x cubed dx. I forgot something. I forgot the dx over here. So when we integrate this quantity here, we get y x squared equals x to the 4th divided by 4 plus c. Now, what are we going to do to get y by itself? So we divide both sides by x squared to get, we divide everything by x squared. So we can cancel these guys right here. So we're going to get x squared over 4 plus c over x squared. That is our final answer. Okay, general solution. Okay, now let's do one that has trigonometric functions and with an initial condition as well. Okay, so notice in this case, the equation is given in the correct form because the derivative term has a coefficient and an invisible one. So first of all, let's identify the p and the q. So this is p and this is q. Let's write them down. P of x equals tangent, and q of x equals sine of x. Okay. So let's evaluate the e to the integral of p dx, which will be e to the integral of tangent x dx. And if we recall from the trigonometry chapter, the integral of, well, it's actually negative tangent, right? Because of the negative sign, we need to go with the sine of it. Okay, so this will be the integral of negative tangent x dx. Let me pull out the negative sign out of the integral to avoid silly mistakes with too many negative signs. What is the integral of tangent? From that chapter, we got that integral to be negative ln of cosine of x. Okay, we can use the Smile rule here to cancel that into a positive. This will be e to the positive ln of cosine. And at this point, we may cancel, we may divide out the e with ln to get just cosine x. So writing down the formula again, notice how this quantity right here, cosine, corresponds to this e to the integral p dx, and let me highlight with yellow the quantity q of x. So let's just replace, so y cosine of x equals the integral of q, which is sine of x, times e to the integral of p dx, which is cosine x dx plus c. Okay, now how are we going to evaluate the integral that we have on the right hand side? Notice how this cosine x dx serves as the differential of sine, because the derivative of sine is cosine. So we are going to take this u equals sine of x and du equals cosine of x dx. And in this case, no adding constants to compensate the differential. We're good to just do y cosine of x equals the integral of u du plus c, and the integral of u du is simply u squared over 2 plus c. And the left hand side remains the same as y equals cosine of x. Now let's go back, substitute for u, which is sine squared of x divided by 2 plus c. Okay, so cosine x that multiplies y. In order to get y by itself, let's just divide both sides, actually everything, by cosine x. Okay, so cancel these cosines, and I know you might be thinking of moving this cosine to the numerator as secant, but in this case we are going to find a particular solution, so it might be easier to leave everything in terms of sines and cosines. So y equals sine squared of x divided by 2 cosine of x plus c divided by cosine of x. Okay, so that is the general solution. Now we're going to find the particular solution. So let's use the condition. Use the condition y of 0 equals 1, which means that when x equals 0, y equals 1. That's what it means. So let's plug in y equals 1 over here. And wherever you see the letter x, the variable x, plug in the 0. Okay, so let's evaluate cosine of 0. We know cosine of 0 is 1, right? That is from c divided by 1, which is cosine of 0. But in this case, the denominator of the first term is also going to be a 1 times 2. But in this case, sine of 0 squared, this is going to go to 0. So we get 1 equals 0 plus c over 1, which gives us c equals 1. So the particular solution, the particular member of the family of functions that passes through the point x equals 0, y comma 1 is this function in particular. Okay, so that is sine squared x over 2 cosine x plus 1 over cosine x. That is particular solution. And general solution. Okay. Let's look at another method of solution. So higher order linear homogeneous differential equations with constant terms. Just the name is really long. The name of the method is really long. However, this is one of the easiest methods of solution because it doesn't even involve any calculus. All you need to know for this method is know how to factor polynomials. That's all you need to know. So we are going to rewrite, okay, a differential equation. We are going to convert that into an algebraic equation, so in which the derivative factors disappear and we put the variable m in this case. For example, look at this differential equation. This is a second order differential equation. So the second derivative of y plus 4 times the first derivative plus 3 times the function equals 0. And we call it homogeneous when the right hand side is a 0. Okay, for the non-homogeneous, we're not going to look at those. Those actually take even pages to solve one example. So we're not going to do that. We just do the basic one, homogeneous one. So this y prime becomes an m squared. The exponent 2 comes from the order of the derivative. The coefficient remains the same. The m to the invisible 1 comes from the first order derivative, and then plus 3. So in this case, no letter for the coefficient that has y without differentiating at all. Okay, the other equation, which by the way, this polynomial equation related to the differential equation, is called the characteristic equation. M squared minus 5m minus 14 equals the 0. And then we look for ways to factor that polynomial equation. So in this case, we're going to have 3 specific cases. So we solve the polynomial equation. And number 1, if the solutions to the equation m1 and m2 are both real and distinct, the solution will be of the following form: c1 e to the m1x plus c2 e to the m2x. No calculus. Convert that only to an algebraic polynomial equation. Solve the polynomial equation. Those solutions will tell us what to do. There are cases in which the equations give a repeated solution, and in this case, notice the solution. They look similar, except for this factor of x that gets added here that is not on the previous case. Also, when we solve quadratic equations or polynomial equations, we may run into complex solutions, complex roots. So for a complex solution, we need to identify the real part of the complex number and the imaginary part of the complex number. And the solution will be as follows. So it will be a combination of sines and cosines. Okay, so c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x. Well, right now it's a lot of symbols and whatnot. So how about we go over the examples so you can see how this works. Okay, let's solve the given differential equation. So number 1, let's write the characteristic equation. So the y double prime becomes an m squared minus y prime, which becomes an m, and then minus 2 equals to 0. Let's solve this polynomial equation by factoring. Factors of -2 that add up to -1. So this will be -2 and plus 1. Okay, so the solutions to this equation, m1 equals -2 and m2 equals to -1. So in this case, these two solutions, notice they are the blue case, two distinct solutions, which is this case right here, the one I'm highlighting again. Okay, so the solution will be y equals c1 e to the m1, which is negative 2, x plus c2 e to the, actually it's positive 2, not negative 2. Let me erase this real quick. That's a 2. Highlight with blue again, and this is getting erased again. So e to the 2x plus c2 e to the negative 1x. That's all we do. When it comes to find the constant c1 and c2, we are going to do an example later. For now, let's get familiar with the different cases. Okay, so let's solve the differential equation y double prime minus 8y prime plus 16y equals 0. So we turn this into m squared minus 8m plus 16 equal to 0. Okay, so we can solve this by factoring again. So factors of 16 that add up to negative 8, negative 4, and negative 4. And look what we have. M1 equals 4, which is also m equals 2. It's a repeated solution. How are we going to deal with this? Well, let me show you the case again. So c1 e to the m1x. So y equals c1 e to the m1, which is 4, plus c2 x times e to the same, and that's the solution to the equation. So distinct and real and repeated. Okay, what about when we have kind of an ugly numbers? Okay, let's write down the characteristic equation for this differential equation. M squared plus 5m plus 3 equals 0. So in this case, if you try to solve by factoring, it's not going to work because there's no way to find factors of 3 that add up to 5. So in this case, let's use the quadratic formula. M equals minus 5 plus minus the square root of 5 squared minus 4 times 1 times 3. The whole thing divided by 2 times 1, which equals negative 5 plus minus square root of 25 minus 12. Subtract the numbers inside of the radical to get 13 inside. So negative 5 plus minus the square root of 13 over 2. So that means that we are going to have two solutions. One, m1, which will be negative 5 minus the square root of 13 over 2, and m2 equals negative 5 plus the square root of 13 over 2. So in this case, we have two distinct solutions and real solutions. I mean, they're ugly looking, they're irrational, but they're still valid solutions. So y equals c1 e to the, okay, how to write this? Negative 5 minus square root of 13 times x divided by 2. Notice because of the 2 in the denominator, plus c2 e to the negative 5 plus the square root of 13 times x divided by 2. And that is the solution to this differential equation. Let's do one more. Okay, the next one. Okay, let's see. Let's write down the characteristic equation. M squared plus 4m plus 5 equals 0. If you try to solve this by factoring, it's not going to work because there are no factors of 5 that add up to 4. So in this case, we're going to use the quadratic formula again. So minus 4 plus minus the square root of 4 squared minus 4 times 1 times 5. Divided by 2 times 1. So negative 4 plus or minus the square root of 16 minus 20 divided by 2, which is the same as saying negative 4 plus or minus the square root of negative 4. But what is the square root of negative 4? Remember imaginary numbers? Okay, so this will be negative 4 plus or minus 2i over 2. And let's simplify this number, these complex numbers, by negative 4 divided by 2, that's a negative 2, and 2 divided by 2, this is plus minus 1i. Okay, so in this case we have complex numbers. So for complex numbers we need to identify what? Alpha, which is the real part of the complex number, and beta, which is the imaginary part. Okay, so in this case alpha equals negative 2 and beta equals 1. Where is that 1 coming from? The number that multiplies the letter I, which is an invisible 1. Okay, so the solution to this type of equation, y equals c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine beta x. So y equals c1 e to the alpha, which is negative 2, x cosine of beta, which is just 1x, plus c2 e to the negative 2x sine of x. And that is the solution to this equation. What about number 5? Okay, let's convert this to the corresponding characteristic equation, but notice the y prime term is missing. Okay, so this is the same as saying y double prime plus 0y prime plus 36y equals 0. So when we convert this to an algebraic equation, a polynomial equation, this will turn into m squared plus 0m plus 36, in which this is simply m squared plus 36 equals to 0. Let's use the square root property to solve this equation. Move the 36 to the other side, and m will be plus or minus the square root of negative 36, which will be m equals plus or minus 6i. Notice in this case we didn't get anything for the real. That is the same as saying 0 plus or minus 6i, in which alpha equals 0 and beta equals 6. So when we construct the solution to this equation, it's going to look like exactly like the previous one, but you will see what is going to happen. So this will be y equals c1 e to the alpha, which is 0x cosine of 6x plus c2 e to the 0x sine of 6x. So e to the 0 power, what is that going to be? Whatever that is, this is going to be 1. It's going to be 1. And the final solution, the actual general solution, will be c1 cosine 6x plus c2 sine 6x. Final answer for this one. Question, can we go higher than 2? Of course. Higher order, that no wonder the title, right, of this section, higher order differential equations. Okay, so solve the differential equation y triple prime minus 8y. So in this case, the corresponding equation, the characteristic equation, m cubed minus 8 equals 0. Careful when solving this equation because we are supposed to have 3 solutions. So I'm going to factor the left-hand side as a difference of cubes. So m minus 2 times m squared plus 2m plus 4 is the solution, is the factor form of this difference of cubes. Recall that To factor a difference of cubes, the formula is a minus b times a squared plus ab plus b squared. Okay, apply this to this polynomial equation, and that is what we are supposed to get. All right, in this case, what are we going to get? The first m1. So m1, which is equal to 2. But in this case, if you try to solve this equation, we are not going to be able, I'm afraid, because there's no way to find factors for that add up to 2. And in fact, this is a known fact from difference of cubes that this polynomial is prime. So that is that we are going to get complex solutions for that quadratic equation. So we are going to use the quadratic formula, and to get 2 and 3, we solve this m squared plus 2m plus 4 equals 0. So minus 2 plus or minus the square root of 2 squared minus 4 times 1 times 4 divided by 2 times 1, which is negative 2 plus or minus square root of 4 minus 16, which is, let me actually go up here. And this will be negative 2 plus or minus the square root of negative 12. Be careful when simplifying that negative 12, because we will need to break up these factors inside of the radical expression in order to find perfect squares. So this will be the same as negative 2 plus or minus the square root of negative 4 times 3. And the perfect square that goes out of the radical is the square root of 4, which is, let's stick with the green color, which is 2. So negative 2 plus or minus 2 times the square root of negative 3. But what about this negative inside of the radical? We can get rid of that negative sign inside of it, provided we put a letter I outside of the radical. So this is how is this going to look like. Let's simplify this. So this will be 2 divided by 2, that's going to be 1, negative 1, and then these 2 over 2 also cancel, plus or minus I root of 3. So in this case, our alpha equals negative 1 and our beta equals the square root of 3. Okay, so let's build a solution for this equation. So for this part, for the first part that we already got, the general solution will be y equals c1 e to the 2x. Where is this coming from? So this guy right here, it's coming from here. Okay, and then plus c2 e to the alpha, that is negative x, negative 1, cosine of beta. Notice here the x is outside of the radical, plus c3 e to the negative x, sine of square root of 3 times x. And that is the general solution to this higher order differential equation. And to wrap up this part of the chapter in differential equations, we are going to solve the initial problem. Notice in this case, we are going to need more than one condition. The higher the equation is, the more conditions that we need. So for a second order differential equation, we need 2 conditions. If we had a third order differential equation, then we need 3 conditions. Okay, so in this case, I'm not going to solve this equation because we can use the answer from example 4. And for that, we got that y equals, let me just rewrite it again, c1 e to the negative 2x cosine of x plus c2 e to the negative 2x times sine of x. Let me make this negative sign be more legible. Okay. Now before plugging in the initial conditions, I'm going to rewrite this equation. I'm going to factor the exponential factor to simplify the calculation. So this will be y equals e to the negative 2x times c1 cosine of x plus c2 sine of x. Okay. All right, so I'm going to use the first condition, okay, the first condition that tells us that when x equals 0, y equals 1. And then when x equals 0, the derivative y prime equals to 0. So we are going to be in the need of taking the derivative of that function. That's why I factored out the e to the negative 2x to avoid doing 1 and 2 product rules, while we can just do only product of one and another function, only a single product rule. Okay, so let's see. Using the condition y of 0 equals 1, which is x equals 0, y equals 1. Okay, wherever you see the letter y, plug in the number 1. Wherever you see the letter x, plug in the 0. Okay, let me uncircle this so it doesn't look hard to read. So the 1 right here equals e to the negative 2 times 0 times c1 cosine of 0 plus c2 sine of 0. Okay, so what is sine of 0? In this case, a lot of terms are going to get, some terms are going to get simplified. This is 0. And in this case, cosine of 0 is 1. 1 times c1, this is just going to be c1 that multiplies the exponential part. Okay, so this will be 1 that multiplies e to the negative 2 times 0, which is 0 times c1. But what is e to the 0? This is the same as saying simply, this is simply 1. But 1 times c1 will be just 1, which c1 equals 1. Okay, so in this case, we already got this, the c1, the constant of integration c1. Now we need to find c2. How are we going to find c2? Well, notice we have another condition here that requires the derivative of this solution. So number 1, find, okay, let me use a different color here. Okay, find y prime. Notice here we're going to use the product rule, in which this is f, this is g. And recall that the derivative of the product rule, fg prime equals to f prime g plus g prime f, or u prime v plus v prime u, depending on your choices of letters to denote each and one of the factors. So what is f prime? That is the derivative of the exponential part. This will be, so y prime, that is negative 2 e to the negative 2x, all right, times g, which is just c1 cosine of x plus c2 sine of x, plus g prime. What is the derivative of c1 cosine x? This will be, I'm going to leave some space here. Well, actually, I'm going to leave it here. So negative c1 cosine x, okay, negative c1 cosine x, oh well, actually not cosine, should be sine, negative c1 sine x plus c2, the derivative of sine, which is cosine x, okay? That times e to the negative 2x. So what do I have here? F prime g prime f. All right, that's what we have here. Okay, let me erase this so I have enough space for the rest of the calculations. Okay, so now let's use y prime of, what is this, 0 equals 0, which means that when x equals 0, y prime equals 0. So in other words, what we are going to do, we are going to replace this y prime with 0, and wherever you see the letter x, plug in 0. Okay, so that's what we do. All right, so this will be 1 equals negative 2 times e to the negative 2 times 0 times c1 cosine of 0 plus c2 sine of 0 plus negative c1 sine of 0 plus c2 cosine of 0 e to the negative 2 times 0. Okay, number one, this sine 0 is going to make this term go to 0. This one goes to 0. E to the 0 is 1. E to the 0 is 1. Cosine of 0 is 1. Cosine of 0 is 1. Okay, let's write one at a time. So 1 equals 1 times a negative 2. This is negative 2 times c1 times 1, which is c1, plus c2 times 0, which is 0, plus 0 plus c2 times 1, which is c2, and e to the 0, which is 1 times 1. Let's simplify to get c1 plus 0 is just c1, so negative 2 c1, and c2 times 1, which is just c2 times 1, which is just c2. But over here we have one equation, two unknowns, but the good thing is that we know what c1 is, but c1, we know it's 1, so we can just plug that in. 1 equals negative 2 times 1 plus c2. This will be 2 plus c2, which equals to 1, actually negative 2. Add 2 to both sides to get c2 equals to 3. Okay, so we get c2 and c1. Now we're ready to write this equation that was given in terms of c1 and c2 with the particular constants. So the particular solution, and let me use a different color. Let me use black. How about that? Particular. This will be y equals c1, which is 1. I'm not going to write the number 1. It's just an invisible 1. E to the negative 2x cosine of x plus c2 instead of a c2, the c2 that we have here. I'm going to replace that with the number 3 that we got from the calculation. 3 e to the negative 2x sine x. And that is the particular solution. As you can tell, finding a particular solution for a higher degree a higher order rather equation takes a good minute. So, and this is all the process that it takes. In some cases, you may need to solve a system of equations with two unknowns for C1 and C2. In this case, we got a simplified calculation because this guy right here ended up being a 0, but there are cases in which it won't be a 0. So, so this is the end of this part of the differential equations chapter rather. So again, we just covered these three briefly explained methods as we went over before. The list of methods is really big, so I will see you on the next video. Okay, bye.